This is the Milky Way on a very dark sky at about 15,000 feet. And you can see this band of light going through the sky. Up until about 50 years ago, pretty much everybody saw this all the time at night. Right now, even as we speak, approximately 75% of the people in the United States have never seen the Milky Way. That's right. The Milky Way is not visible to most people. And maybe you'll see it tonight if the clouds clear. Maybe. But not like that. That's a long image. No, you'll see it as a faint glow. So I'd like to actually put as an important thing. Back in 2009 was the 400th anniversary of the development of the telescope by Galileo Galilei. And what he did is he basically took, he learned about this concept of the telescope, about lens grinding, from some Dutch inventors, and he said, I can do that. And he started grinding lenses, and he put them in a way such that when you take one lens like this and one lens like this, and held them very steady, they magnify the image. And so what he did is he simply magnified the image with this first telescope. It's made of wood and leather and paper, not metal, nothing like that. The first one was constructed by hand by him. And so this is the end that it looks through. This is the far end. It's at the top there. And there's only 2 of these left in existence. And this one was at the Franklin Institute. My wife, Donna, back there, she and I went to see it in 2009 during the International Year of Astronomy. And when we went to see this thing, it's one of 2. And they have never left Padua, Italy, ever, in 2009. And this telescope's only stop was in Philadelphia. And then went back to Padua. And that's what it looks like. You can see the paper is kind of coming off, but it's all hand-scrolled, handwritten, bound in leather and paper. So what did he look at, and why was it important? So what did he notice? I just said the stars. I mean, what are some basic movements in the sky? And this is where you talk a little bit. So what are some basic movements of some basic objects in the sky that you see, that you've ever seen? Somebody raise your hand. Yes?
The celestial objects like the sun, the moon.
And what do? What does the sun do? Rises in the east, sets in the west. What's another thing that happens? Eclipses. Oh, that's a rare thing, but yes, that occurs too. Solar and lunar eclipses. What's another thing that happens? There's some that are obvious. Let's go with the really obvious ones. Stop. Yes.
Lunar phases.
The phases of the moon. Those are obvious, right? But they're predictable. They always go in the same order, right? Always. What's another thing that's obvious?
Planets.
The planets. Well, there's 5 bright lights in the sky that seem to move with respect to the stars. How about the stars themselves? How about the stars themselves? What do they do that's unique compared to everything else?
Twinkle. Light up the sky.
Twinkle. Light up the sky. They light up the sky. They move, but how do they move? Around the North Celestial Pole. What's another way of saying that? They rise in the east and set in the west. But do they change position with respect to each other?
Yes.
Over the course of a human lifetime? No. Over the course of 10 human lifetimes?
No.
Approximately no. 100 human lifetimes, now we're getting something. But over the course of recorded history up until the 20th century, they didn't. I mean, you really think about it, they can see these things, but they're very tiny motions. We call that stuff proper motion, but let's ignore that for now. The point is that the stars appear for every generation to be the same stars. So we got all these things, rise in the east, moon traverses around the sky, Mercury and Venus, oh, I forgot about that. They're close to the sun in the sky always. Mars and Jupiter go around the whole sky. And all the stars stay fixed with respect to each other. That's a big one. And the sun moves with respect to the stars over the course of the year. So these are some basic things that everybody saw in Galileo's time, and everybody knew about, and nobody disputed. So the point is that everything changes on Earth. So in the sky, when we look at the heavens, the stars themselves, if you talk to your grandfather, and you talk to your great-grandfather, and you listen and you read the stories of your great-great-great-grandmother, and her great-great-grandmother, they will all tell the same thing. So it sounds like that's a unique thing, that the sky is unchanging. All the actions are always the same. They saw it hundreds of years ago. The lunar eclipses, the lunar phases, the rising and setting. The stars have the same patterns over the course of much of human civilization. But in the course of your lifetime, you see trees grow and die. You see people come and go. Children are born, children get old, children of all ages, right? So, but things on Earth change rapidly. So, Galileo, back in 1609, was up against an enormous idea that the Earth was different than the heavens. Meaning the laws and ideas that govern what happens on Earth are different than what happens in the sky. Because nothing ever changes in the sky. That's right, just like that. But everything changes on Earth. Everything. The clouds change. The birds grow and come. The seasons come and go. So that's a funny thing. So everything changes. So why are they different? This is important. This gets back to the fundamental ideas. In medieval philosophy, medieval thinkers said that the heavens are distinct from the Earth. The Earth is not the center of the universe. It just happens to be the place where we're supposed to be. Because the heavens above are eternal and perfect. That's medieval, we're talking medieval Christian thinking. Medieval Christian thinking held that the heavens were immortal, immutable, unchangeable, fixed. We know what they'll do. Everybody's seen them for thousands of years. But everything changes on Earth. So the two worlds are different. And the heavens are where everything is perfect and wonderful and glorious. And therefore that's where you could put your favorite creator of choice up there if you wish, but everybody always did. Notice how every religious gesture is directed towards, when you see a priest or a minister, they're always doing this, okay? It's very interesting. So all religious gesture is directed upwards towards the sky. As a side note, as you lose the night sky, you lose your religion. Now, let's go way back in time. The second century before the Common Era, Ptolemy, which is a Greek mathematician, devised an idea because he wanted to know, and everybody was asking him, okay, how does this work? Because the stars rise in the east and set in the west, these planets move, the phases of the moon, everything's like that. And he said, well, it's my job to figure this out. So he did. And because the Earth doesn't seem to be moving, everything seems to be going over the top, it's perfectly logical. It's absolutely logical to begin with the idea that the Earth does not move. It's a beginning point. And this is 2nd century before the Common Era. It's over 2,000 years ago. So, this idea held sway until 1610. And what does it encompass? The Earth is the center, the moon goes around it, Venus goes around it, the sun goes around it, Mars goes around it. Oh my. Mars. I know, Mars. All the planets, everything goes around it. The stars don't. The stars actually go around on these spheres. That's right. So we have these crystalline spheres. Ptolemy and Aristotle came up with this idea that the crystalline spheres were what the stars and the planets rode on. And as they moved, the planets on them moved. We can't see the crystalline spheres. They're there, but we can't see them because it's perfect and it's another world. right? The heavens are another world, they're not like Earth, so we can't see them. That's fine. It's perfect up there. So the stars, though, have the primum mobile, the prime movement, meaning all the stars move around in the sky 24 hours. So it's really interesting. They tend to drag all these things with them. So this Earth-centered universe was what they knew. Now the problem was that as they were doing this, Ptolemy had to devise all sorts of kooky, wacky stuff, because Mars does this in the sky. Okay, so if you were to put a bunch of stars in the sky, let's say they're all here, I'm just going to make up, like, put them here, like in line, right? Okay, so they're there. I've placed them there. Now I'm moving Mars across, and we take a picture of where Mars is every night. And we see it moving night after night across the sky. It does this. Planets, the word planet doesn't mean a place you can beam Kirk and Spock down onto. Planet means wandering star. Las planetas are the wandering stars. That's what that word comes from. Planetas means wanderers. So they're the wanderers. They're the wandering stars. So as they wander through the sky, they wander in very specific ways. And they do something really weird. Imagine if they did this. Okay, they're moving. But now imagine that they did this. Start over. A do-si-do. A nice little do-si-do in the sky. How did that work? Well, Ptolemy said, as Mars goes around the sky, it has another crystalline sphere that's embedded on top of the crystalline sphere that it goes around on. Now, this is okay, because the Earth's at the center of everything. Now, why is the Earth at the center of everything? We'll get to that. It just seems logical, because we don't feel like we're moving. And guess what? People back then knew that if you were riding on fast on top of a horse, you could feel it, right? Or if you're riding in a ship, you knew it because you saw the horizon moving away. They knew that movement had an effect. So if you were moving, if the Earth was moving, then there should be some effect. That's what they thought. So nobody saw any effect, so hey, we're not moving. We must be at the center of all this. Yeah.
Did anybody ever imagine those spheres as being flexible?
Well, they never really discuss what they mean by crystalline, and they never discuss, well, they have to be flexible because they have to be pass-throughable, right? So there's something about them. But remember that we're making up a mathematical construct that's the perfection and the harmonies of the heavens. It has nothing to do with the laws on Earth. This is a weird thing. We don't think like this. We don't think like this. That's not 21st century thinking. This is medieval and ancient thought. Ancient. So eventually, there had to be epicycles on top of epicycles on top of epicycles. Things, spheres on top of spheres. It's very complicated. You did not want to take a celestial mechanics course in the 15th century. You got, because you know what? Mathematics as we know it hadn't even been invented yet. It was invented in the 17th century by Newton and Leibniz. And Hooke, yes. Yes.
What did the ancients think of transient phenomenon, like new stars that would appear and comets?
They were always bad portents. Comets were bad things. New stars were bad things. In fact, the title of the play Hamlet by William Shakespeare, the title of the play Hamlet is not the tragedy of Hamlet. It is the disaster of Hamlet, and disaster is Latin for bad star.
Really?
And in fact, in Act 1, Scene 2 of Hamlet, by yond new northern star, Horatio. Google that. Second, and get even better than this, Rosencrantz and Guildenstern, if you really want to go there, were kinsmen of Tycho Brahe. And Elsinore has an observatory on it. And Elsinore is also where Tycho Brahe did his stuff. There's some links there. Now Shakespeare knew Rosencrantz and Guildenstern. They were chatty, thus the characters, and he killed them. Anyway, so it ended up that people really had no idea what the heavens were like. Here's a model of the universe by Johannes Kepler, and it's really tricksy. You gotta go, oh, I really didn't want to do this. But he was dedicated. So, all of medieval Christian thought had this grand melancholy. Here's the demon of melancholy, the perfection of the ancient. This is an Albert Dürer from 1510. So, The problem is that all of these measurements and all of Ptolemy's ideas, they had to be rejiggered every 30 or 40 years. Because the predictions of where they would be according to these models, all the predictions of the models would be wrong after about 20 or 30 years. So they had to redo the measurements and redo everything and reestablish where the crystalline spheres were so they knew it. So they knew something was wrong. Now, then comes along this guy, Copernicus, who says, you know it's a whole lot easier if you put the sun at the center? It's a lot easier. It doesn't really make sense. In fact, he was considered a heretic for it. He did not publish his work until he was dead. He published it posthumously. It was nothing he wanted out during his lifetime, because people were being burned at the stake for talking like this. Imagine that. Saying that the sun was at the center of the solar system could get you killed. You think we got problems saying, you know, if you go to Iraq or something like that. This is an even bigger problem. This is a really big problem because it's not really a thought police, it's just such a highly unaccepted thought in terms of theology that it was a big problem. But what did he say? He simply said that let's establish as a mathematical idea to help understand what's going on. Put the sun at the center and see what you get. And in fact, Copernicus's ideas and Copernicus's models did exactly as well as Ptolemy's. They did not do better. They weren't, the results from his models of having the sun at the center, according to Copernicus, did no better than Ptolemy. Why? Because what Copernicus did is he said that all the planets move in perfect circles. They don't. They move in ellipses, as we learned from Kepler later. But the point is that that's why Copernicus's ideas didn't immediately catch on and go, oh yeah, it works. Because his ideas didn't make any better predictions than anybody else's. Tycho Brahe even made up a prediction where the sun was at the center, but not really. Well, it's Earth-centered, but the sun kind of had stuff going around it too. So he made a mixed version. Now, this has some interesting predictions. And one of them is very important. It bases it on, the sun-centered universe has a basis and gives predictable results. So, what are they? Well, if you have the sun at the center, and Mercury, Venus, and this is his actual drawing with the Latin in it, Venus, Earth, with the moon going around the Earth, this was never up to dispute. That the moon orbited the Earth was never up to anybody's dispute on any level. That's interesting. Nobody ever said this. Even Copernicus, look at this. How did it stay in orbit around the Earth? Orbit. The concept of orbit wasn't even really in. In fact, the concept of an orbit had to wait for somebody like Kepler, which was later. But this was just the motion. This is the model. And this is what we mean by a model. A model simply is my idea put on paper so that I can show you what I mean. And I can discuss this phenomenon cogently to you. Why put Saturn way out here? That's because it moves very slowly with respect to the background stars. So Saturn must be far from the center for it to move slowly. Why put Mercury close? Because it has to be close to the sun, because as we look at the sun from the Earth, it's never very far away from it. So it must be closer. So a model gives predictions and ideas by just drawing itself. And Copernicus made even a more flashy-looking version. This was his 2.0 version, right? The one that was designed for web use. And then something came along. Galileo was not convinced that Ptolemy was right. Now, he didn't know whether it was right or not. He just didn't like these ideas. He was an upstart. He really had attitude problems. I mean, by attitude problems, he did not play well with others. He really did. And what it ends up happening is that in 1609, he does something unique. He builds this, a telescope, which we saw before. He was not the first person to build a telescope. There were others, but he was the first person to write about it. And he actually sold his telescope to the Venetian Senate about a few months before a shipment of telescopes came in from the Netherlands. So he also knew how to sell things. He was a salesman. In fact, that was one of his both one of his great assets and one of his reasons for his downfall. So, what did he do? His telescope was different. And let's look at what it did. And why this was such a unique idea. He looked through the telescope and he drew what he saw. Wow. But yeah, wow. No, really. Nobody's ever done it before. What happens when you look through a telescope? It's brighter and it's bigger. There's magnification and it's brighter if the telescope is built. You can build a zero-power telescope. It's called a toilet paper tube. That's a zero-power telescope. No, well, 0 times power, right? Oh, right, exactly. It's a zero magnification, but it's a one times power telescope. Exactly. It's a unique power. But what he did is that notice the point that he's doing. Medieval Christian theology held that anything that was based on the materia of the earth, I didn't say the word material, I said the word materia for a reason. Materia of the earth was by necessity of the earth, and was by necessity part of that which can be corrupted. Now we're getting into the theology aspect of this. The heavens are incorruptible, unchangeable, and perfect. The earth is corruptible and changeable. He makes a telescope out of elements from the earth. Sand, melted down. The sand then gets made into a piece of glass. The glass is then ground by hand. You put the 2 pieces of glass that have been ground by hand inside a tube, you look at it, things make it amplified. That's using the products of the earth to study the heavens. Theologically, that's a problem. Because you're using something corruptible to study something that's uncorruptible. So how can you trust it? It can fall apart. It can lie to you. These are words that were used to debate Galileo when he looked at the sky. So, when he drew and looked at the sky, everybody was perfectly happy when he was looking at a ship coming over the horizon. Because what was he doing? You say, oh, there's the ship. It's coming over the horizon. I can see it 5 miles before anybody else can, because you're looking at a ship. A ship is made of material from the earth, so who cares? It's earth looking at earth. Looking at the heavens is different. So, when he looked at the heavens and drew this, the moon, and you've all looked at the moon through a telescope. You see craters, you see mountains, you see valleys. That is unique. That shows that the moon is like the earth. But it's up there in the heavens. So the moon and the earth are the same kind of thing. That's what Galileo's trying to say here in this picture. And then he also said, look at this picture I drew of Jupiter. It has 4 little stars around it, the Medicean satellites. Oh, he was trying to get a job from the Medici brothers, and he got it by naming them the Medicean satellites. I would like to name these after my great patrons, the Medici, and he named them after them. But we call them the Galilean satellites, not the Medicean satellites. Very interesting. We renamed them away from the names of the brothers that he actually named them after, the 4 brothers. It's wonderful. It's impossible. But that's what you get if you lived in Tycho Brahe's universe. You'd have the Mars coming inside the moon's orbit. It would be a bad day. So that doesn't work. So there's this thing called angles. I'll skip it because this is not a college class, right? So here we go. Skip. But the real point is that, okay, the big problem that people had with Galileo's idea, because Galileo said, okay, there's 2 problems that they have. One was a physics-related science question of the day that was valid. And the other one was not, was a theological argument. I will tell the theological argument while you look at this picture. The theological argument that the earth should be at the center is the following. And all you have to do is remember Dante's Inferno. Dante's Inferno had the following. Virgil and Enid went into the earth, and went down and down and down. And every layer they went down, further down, they got closer and closer and closer to the devil, at the center of the earth. Wow! That's Dante's version. And and it's not in Christian theology. Dante just had it out for a lot of people in his hometown because he was actually kicked out of town. So he basically wrote a nasty thing saying, I hate all these people, here's all these people, I'm putting them down. It's true. There's like hundreds of people that he hates, and he put them all in his book. It's hilarious. So anyway, he put this in there, and the point is that, but it fit perfectly with medieval thinking, is that which is corrupt and evil is in the earth. So therefore, if the earth is orbiting the sun, it is closer to the heavens. And it is hubris for man to think of himself as of part of the heaven or even closer to heaven. We're closer to that guy down below the earth than we are to heaven. So if we move the earth out of the center, we get closer to God, and that is hubris. And that's blasphemy, which is really interesting. And that's a theological argument in favor of geocentrism. Now, it's nothing to do with anything physical, because here's the thing that really clinched it. The scientists of Galileo's time said, okay, so if the Earth is moving, why don't we see the stars wag back and forth as they go back, as they move, as the Earth goes around? Because the Earth moves around the sky, it has a different perspective on the stars. So we should see stellar parallax, meaning just in the same way that, everybody do this please, take your thumb at arm's length. Now, close your eye, back and forth, and go like this, wag your eye one thumb at a time. You see your thumb moves with respect to, his thumb seems to be moving, everything behind it doesn't, right? Because you're looking at it from two different perspectives. That's parallax. So now, here's the idea. The thumb is the star, there's other stars way over there, your nose is the sun, and this is the Earth's position in June, and this is the Earth's position in December. Blink, 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 the stars move. That's this. That's stellar parallax. That is not observed, or at least not by the technology available to the people in Galileo's time. It took until the 1800s before somebody could actually see this. And the first star seen was the star that was seen by Sir William Bessel in the 1830s, and it was 61 Cygni. And it's 11 light years away. But it's such a small change in angle. This is a huge change in angle. It's the width of a pizza slice in New York City as seen from here. That's how small the shift is. Very small shift. Very small shift. So, this is a real effect though. If you have really good photographic techniques or a really good eye, you can see nearby stars that shift with respect to the background. Stellar parallax is a proof that the Earth moves. Yes?
When did you say that was first observed?
1838, I think I put a slide up, and did I? Oh, there's a parallax defined, and let's go forward one more because I think I put a slide in there. We go, 1838. 1838 Sir William Bessel. And Bessel was one of the great physicists of our time, and it's also a variable star. For those that want to do something really interesting and watch it, it's actually a binary system where the two stars are actually flaring and doing neat stuff together and orbiting each other. It's really kind of a beautiful binary, and it looks like this in a large telescope. It's a double star, and they're variable. So the shift is 11,000 times smaller. Okay, hold your thumb at arm's length once again. The width of your thumb is 1 degree, according to your eye held at arm's length. That means that to do this, you'd have to go 1, 2, 3, 4, 5, 6, 7, 360 times in order to get all the way around. Wow. You could do that. Have some fun. So, what do you get when you measure stellar parallax? Let's jump forward. How Galileo changed the world. He had some problems with the church. He was nearly excommunicated. He was sent into house arrest for the rest of his life. By being sent into house arrest, he published his great works of physics. And when he did that, those works were later used by Newton to understand gravity. In fact, if you read the dialogue concerning two world orders, he's this close to getting this idea of gravity. He's just one step. And the reason he doesn't get gravity is because he's too busy mocking people. He's surfing the web. basically taunting people, basically attacking people. And as you read it, his physics is glorious. His ways of thinking are amazing. But he was so caught up in the attacks of his time on him and the ones he was doing on people that he actually missed the concept of mass. And you can see it in his writing. It's almost there, which is really cool. But it's like, I almost got Easter. No. It's like I'm teaching physics, right? And I'm having my students write a paper on gravity, and they go, oh, B. We got a B. Galileo got a B. But for his time, he got an A. Because when he did that work, when he finally actually was under house arrest, and his daughter, who was a nun, actually helped him edit it, and probably wrote most of it, because he was going blind and having cataracts, she probably did all the writing. There is some reason to think that his daughter, Celeste, was at least as intelligent and at least as gifted in mathematics and physics as he was. But yet, because of where she was in time, the only opportunity for her was either to become married, and possibly with a 25% chance of dying in childbirth, which was very common back in that time, or becoming a nun. Those were only two options in life. She chose to become a nun because at least she could think. So now, if we can finally get past and actually look at Galileo and look at his accomplishment of actually taking the data and pushing it to people and demanding that they look at the data, not say what Aristotle said a million times 2,000 years ago, not trust the words of somebody. I trust you. No, it's not good enough. It's not good enough to trust. Go look. Go measure. Go see. That's the law. That's only one law of science. When somebody says something to you, you say, okay, show me how you did it. And a true scientist will say, okay, I know I made some mistake here. They'll be all of a sudden, and they'll be defensive because they're a person, right? You know, you don't want to be attacked, right? Right? But the thing is that if you're honest, you say, oh, that's great. Show me where I went wrong. They'll roll up their sleeves and get down to work. And when you get down to work and finally look at the stellar parallaxes, and you send up a satellite, such as was done in the early 1990s, and measure the parallaxes of over 100,000 stars, and get their distances, and second, get a measure which gives you how far away they are, and then you look at how hot they are, the surface temperature, meaning the cold ones are here, and the hot ones are there, by looking at how bright they are at certain wavelengths and certain frequencies. And then you say, because I know how far away they are, and I get how bright they are in the sky, I know how bright they really are, meaning their luminosity. I can say how bright they really are here because I know how far away they are, and I can plot their temperature versus their absolute brightness. And I get this plot of stars, which is called the main sequence. It's a fundamental discovery of astronomy. A fundamental discovery that 75% of all the stars fall along this little pattern on this graph. It's called the HR diagram, discovered in the later part of the 19th century, early 20th century. And we see white dwarfs down here. They're very small and very hot. Main sequence stars. Our sun is one. Giant stars like Betelgeuse is up in the sky. Some other bright giant stars that you might see in the sky tonight. We'll look at some. But the point is that they all fall here. And this is a fundamental property of all stars. How they are on this plot, where they are on this plot. This is the beginning of physics. This is an element of physics. So when Galileo said, I will point my telescope at the sky and take measurements, he was the first physicist. By saying, oh, I'm going to go see what's happening over there. And he said, and he opened the door for Newton's idea. And Newton's idea was, the laws of physics on the earth are the same as the ones in heaven. That's heresy. That's blasphemy to medieval Christian thought. The laws on the earth, hold that thought. I won't forget you. So the laws in the heavens are the same as the ones on earth. Because the stars are just like our sun. The moons that orbit Jupiter are like the moon, our moon. The moon around the Earth has craters and mountains and valleys just like the Earth. Wow. And all those stars in the sky, all those prickly points, they're just really, really, really far away, but they're the same thing as the sun. So this is a divide, a fundamental divide. We had these two universes, the materia of the Earth and the celestia of the heavens. Two universes were divided. But when the measurements were taken, and you used the ideas and the observations, they linked the two and you put a bridge. And that bridge was then formalized by Newton with the laws of motion, the laws of gravity. Fundamental ideas. And now, we don't think of planets as wandering stars. We think of them as places for Kirk and Spock to build a ship, to go over there and get to them. It's not surprising to us. So when Curiosity lands on Mars and goes, wow, look at this rock, nobody's surprised. We've seen the rocks on Mars a bunch of times from Viking and Sojourner and Spirit and Opportunity, and from Mars Reconnaissance Orbiter. We've seen it. It looks like a place we could go to. That's not ancient thought. We are so different now. We've changed. And the element of change is it doesn't, and the funny thing is notice that Galileo, even through the last part of his life, he considered himself to be one of the most devout Catholics of all. He trusted his church, he trusted his priest, he trusted his friend the Pope, even as he insulted him. He trusted him. He abided by his edict. He said, you will be under house arrest. He allowed himself to be part of that. He did not rebel. He wrote instead. So there is no conflict. There's no conflict in Galileo's mind between his faith and his science. There's none. And even in today, there's none. Except if you literally take the word, the capital W, right? And you say the purpose of the stars is to illuminate at night, and that the earth is at the center. Picture biblical scripture. Literal readings don't work. Fundamentally. We have to interpret. Because, wow, it gets all weird. So the theology is that we have this, I'll finish it with this interesting idea that I'll let you munch on while you're out looking at the stars. There are three different kinds of thought. The first we will call mathematical thought, logic. You start from axioms, and from those axioms you prove things. And what you prove in mathematics is truth. You just go take a math class. They'll talk truth, axioms, and these are truth. Only in mathematics do you find truth. Now, you have another kind of knowledge, and that we accept as humans. It's called revealed knowledge, where you start with articles of faith. And these are all the great religions, and even the not so great, even the minor ones, the major ones, the ones that have gone, the ones that are still to come. We'll have articles of faith that we say, they may be absurd, but we say, I believe. And then you start from there, and that gives you your religion. Those are revealed knowledge. We accept that. But you can logically flow a whole bunch of things from revealed knowledge. Then we have the third kind of knowledge, which is empirical knowledge. Go out and stick a fork in it and see if it still is moving. Measure it. Take a measurement. See how big it is. See how far it is. See how massive it is. How strong is its magnetic field? Does it have enough spin? Wow. What's its quantum state? Does it exhibit the Hall effect? Is it degenerate neutron matter? Wow. Is there an event horizon? All of these things. These are all questions that we have that we would answer with the concept of natural philosophy. Measuring things and learning by looking at the world. There are three different kinds of knowledge. There are three different approaches. They're mutually incompatible. They inform each other, but yet they teach different things. And Galileo was the first person to lead us down the concept of let's actually do this empirical knowledge thing. There you go. Let's go and get some stars. If you have any questions, I'll be happy to take them up here. But otherwise, please, it looks like it's dark out. Oh, a question right here, yeah.